we started the discussion on regenerative feed heating, and we also discussed the ideal regenerative feed heating system, where the feed water heater from the feed pump was heated reversibly to the temperature equals to the saturation temperature to the boiler pressure, and this way the Rankine cycle was made equivalent to a Carnot cycle. But at the same time, we appreciated, this is the way we understood the philosophy of regenerative feed heating, by which a Rankine cycle is converted to a Carnot cycle, means the heat is added to the maximum temperature of heat addition. Because the sensible heat part, that means the heating of water from a temperature lower than the saturation temperature at the boiler pressure up to the saturation temperature, was made possible by the internal heat, that means the heat of the expanding steam. But at the same time, we appreciated the practical difficulty of obtaining so, because we cannot place a heat exchanger in the turbine, number one. Number two, a reversible heat transfer to achieve a temperature that is equal to the saturation temperature of the water at the boiler pressure, which is equal to the inlet temperature of the turbine, is not possible. And last but not the least, one of you mentioned that the drainage fraction at the end of the turbine expansion in the turbine was also reduced. So, for all these reasons, this particular ideal regenerative feed heating system cannot be obtainable in practice. This is purely a concept. So, what is done in practice, the feed water is heated, because it was understood that if we can heat the feed water to some temperature by taking the heat from the steam, then we can increase the efficiency of the cycle, because the mean temperature of heat addition is increased. So, what is done, the heaters, the typical heat exchangers are made outside the turbine, and the steam from the turbine at different pressures while the steam is expanding through the turbine is bled, and what happens, that heat from that steam is being transferred to the feed water passing through the heater. And there are two types of such heaters. In one heater, the steam and waters are being mixed together, so that they are under same equal pressure, otherwise the mixing is not possible. And in another type of heater, this is known as closed heater, the steam and water, they do not mix with each other, and water is at some pressure and steam is at other pressure, and there is a separating wall. They water flows through a tube, steam is condensing on the surface, the way they exchange the heat transfer. So, the closed heater is beyond the scope of our study, the present moment. Only we will discuss the open heaters, which are relatively simple than the closed heaters. So, we will discuss the closed heater system, which is implemented in practice for regenerative feed heating. Feed means the feed water, and regenerative means we use the heat from the system itself to heat the system from one part and to heat the other part of the system. That is the definition of regeneration. So, now we come to this closed heater. So, the diagram is like that. Let us consider this boiler here, and the steam enters at some pressure and temperature, the boiler pressure and temperature at this point 1, and this steam expands up to the condenser pressure 2. Okay. Then I just draw this figure like this, not here 2, that is be better. Let we consider this point 2, that means steam after expanding to a pressure corresponding to 2, some amount of steam is bled for the regenerative feed heating. Let us consider the analysis for 1 kg of flow at the inlet to the turbine. Let here the flow rate is 1 kg at 1. Then at 2 correspond to certain intermediate pressure, after which, when the steam, after which the from the point 2, after which pressure the steam being expanded, some amount is being bled. Let this amount equals to well, I think this point 2, 3, just wait, 4, 5, let this mass is M2, let this mass is M1, which is being bled from this point 2. Now, let the steam expands to another point 3, where another amount of mass, that is M2, is being bled. Then the steam expands to the condenser pressure 4. Then after condensation, this point is 5. It does not matter the nomenclature. Sometimes people go to this point with 2, does not matter. Then what happens? You see the system. So, therefore, at 4 we are having 1 minus M1 minus M2 kg of steam. So, from 2 to 3 the expansion of steam taking place whose mass is 1 minus m1 per 1 kg of mass at the inlet to the turbine. I am analyzing this thing. Then 3 m2 mass is bled, then 3 to 4 final expansion takes place 1 minus m1 m2 kg mass. So, this 1 minus m1 m2 kg of mass is condensed at the condenser pressure. So, that is 4 to the 0.5, that means it is condensed to the saturated liquid. Then what happens, there are 3 feed pumps. First feed pump pressurizes this saturated water to the 0.6, this 0.6, which is equal to the pressure 3. Why? Because this water is being pumped, this is to this heater H2. So, therefore, this 6 is the pressure corresponds to this 3. That means, it 4 and 5 are the same pressure. So, 5 to 6 is the pressure rise, that means it goes to this pressure. Then what happens? We get, so if you consider this heater, you see it receives steam M2 at pressure P3 and temperature T3. It gets water at same pressure, P6 and P3 are same, but at different temperature. So, it is the water entry. So, both of them mix together and we get, therefore, if M2 is mixed with 1 minus M1 M2, we get 1 minus M1 kg of water, which is at the same pressure, because mixing is taking place at the same pressure, which is being pumped. That means, this 3,6, this point is 7. After pumping, this point is 8, that means this is 8. Okay, this is being pumped to this pressure, then it goes, this becomes 9, and this is mixed with M1. So, ultimately this becomes 1 kg, which is then pumped 10. So, this will be more clear if we see the diagram here, TS. Now, let us follow. This is the one. After expanding to the point 2, we bleed M1. Then 2 to 3. So, therefore, here it is the expansion with 1 kg, 1 kg. Then 2 to 3 expansion is 1 minus
Sir, please go a bit slow.
M1 kg. Please ask question.
Sir, please go a bit slow.
Slow. So, 3 to 4 is the 1 minus M1 minus, I will repeat it again, M2 kg. 1 minus M1 minus M2. Well, then at 4, this is 1 minus M1 minus M2 kg. So, this comes to the point 5. Now, 5 to 6, this is 6, this point is 6. So, what happens? This enters here 6, that means this liquid is heated, whereas this M2 steam which is bled at this pressure is being condensed. You understand? That means the steam is condensed, the M2 amount of steam at this condition is the entry to this heater, whereas this is the mass 1 minus M1 minus M2 kg of water at condition 6 is the inlet to this heater. So, the outcome of this heater, this is the point, this point corresponds to 7. Clear? So, what will be this point? Please tell me. This point corresponds to which point? 8. Obvious, this point is 8. This point is 8. It is very difficult to write, though I am drawn this, these are very close to each other. This point is 8. So, 8 and here this M1 kg comes to, so therefore, this point corresponds to the 9, which is the outlet of this heater. Then this 10. So, this line corresponds to the pressure P2, this line corresponds to pressure P1, that is the boiler pressure, and this line corresponds to pressure P3, the second bleeding pressure. Clear? Clear? Now, you see, if I write the expression for work of the turbine, last class one of you asked this question, I was very happy, work is reduced. Per 1 kg, if you see that work done is H1 minus H2, that means the mass is changing. So, I am writing work per 1 kg of steam entering to the turbine plus 1 minus M1 into H2 minus H3, clear, plus 1 minus, because this part is associated with 1 minus M1 minus M2 into H3 minus H4. Clear? What is heat added? Heat added. Heat added from outside source. That means it is, because this is 1 kg, again it is 1 kg, that means H1 minus H10. So you can find out it as WT by Q added. You can find out many things from this. So this is the analysis.
WT also WT minus WP.
WT minus WP. You are very, very correct. So what are WPs? Let us write here. The space is so short, that is the problem. WP, please tell me what are WP. Now see, here the amount is 1 minus M1 minus M2. So this pump handles 1 minus M1 minus M2. So therefore it is 1 minus M1 minus M2 into H6 minus H5. Very simple. Just slowly you have to follow. Plus this pump handles what? Now here 1 minus M1 minus M2, it mixes M2. So that here at 7, that means M2 steam is cooled and 1 minus M1 minus M2 steam is heated. So it is heated to saturated liquid, it is cooled to saturated liquid. That means it is condensed, it is sensibly heated to its saturated temperature. So that it becomes 1 minus M1. So therefore this pump handles 1 minus M1, 1 minus M1 into H8 minus H7, H8 minus H7 plus, very good. Now here you see that is 1 minus M1, this pump ho gaya. So therefore it comes 1 minus M1. So therefore this is the point where it is heated to, oh kya hua? Oh, this is all right. 1 minus M1, sure. So this comes here. Now it is 8 entry, these 2 points are repeating, that means the 2 are the same point, there is no process here. So therefore it is heated to 9, 8 to 9, sensible heating to saturated liquid, whereas M1 is condensed. And when they mix together, as a result we get at 9, 1, because M1 is added. So 9 is the 1 kg here. So therefore this pump, feed pump 3, handles 1 kg. So this is plus 1 into H10 minus H9. So this is WP. The sole problem or the main problem of calculation is M1, M2. Otherwise everything is clear. So the main parameters are how to find out M1, M2. How to find out this. If I can find out M1, M2, I can find all these things. The analysis is based on 1 kg at the entry to the turbine, and I can find eta. Clear? How to find out M1, M2, please? How to find out M1, M2? M1, M2, how to find out? From the energy balance of the heaters. Let us consider first the energy balance of this heater. Control volume. What is the energy balance of this heater? Energy coming in M1, H2. You see here, not when you write the energy balance, you see the block diagram, not the cycle diagram. Other part, this is what? Here the space is short, you can write the amount. That means this is 1 minus M1 kg. This is 1 minus M1 kg. This handle, this line is 1 minus M1 kg. That means 1 minus M1 into H8. What is the outflow? This is 1 kg. 1 into H9. So this equation will explicitly give me M1 provided I know H2, H8, H9. Let us find out. What is H2? H2 is this point. This will be clearly told in the problem. That means if I know the bleed pressure and it is an isentropic expansion, I know H2. And if I am told there is an isentropic efficiency up to expansion of this bleed pressure, then also I can find out H2, the actual H from the isentropic efficiency. Usually it is told isentropic expansion. By isentropic expansion I can do it straight from Mollier diagram or from steam table. That means I know H2. Ho gaya. What is H8? H8 is the, where is H8? H8 this one. This point is H8. Mind that this point is H8. Clear? This point is H9. Let us first H9, simple. H9 is similar that this, at this pressure, the enthalpy of the saturated liquid, H9. So I will have to know H8. Okay? How to find out H8? Can anybody tell?
Sir,
H8 minus, no, not temperature, H7,
equal to
because H7 I know. H8 I do not know, it is a subcooled state.
equal to
It is
P8
better the
minus
work
P7
done. Yes, very good. It is P8 minus P7
into V7.
into V7. There is a little bit trick here. I know P7 because I know the next bleeding pressure. I know P8, that means this pressure and this pressure I know, and the specific volume at this bleed pressure I know. So I know H8. Clear? So I can find out H8 from here. So I know the H8. Another way of knowing H8 of course is there. If you know the temperature for water, you can calculate that as the kilojoule per kg, that you can multiply with the Cp and you can find out the what we call, we can find out the enthalpy of the water. Actually what happens, the enthalpy of the water is taken 0 at its saturated state at 0 degrees Celsius. Then if you consider saturated state at 0 degrees Celsius, means the pressure is very low. It is almost 2.0006 bar. So at this pressure, if you heat the water from 0 degree to any temperature T at constant pressure, then Ht minus H0 is per unit mass Cp into T. So if you put the reference H0 as 0, then you can tell that temperature at any temperature T, the specific enthalpy is Cp into T. You understand this thing? Now you can tell that it is at this pressure, because our reference is at this pressure, but if I heat the water at different pressure from 0 degree to any temperature T, then I cannot put the reference enthalpy at 0 temperature, but there the answer is the influence of pressure on change of enthalpy is negligible. So therefore you can approximately put the value of enthalpy 0 at 0 degrees Celsius at any pressure, which means at any pressure temperature T is its specific enthalpy. Sorry, Cp into T is the specific enthalpy. So that is another way of doing. This is also another way of doing, and these two are very close to each other. Okay, your concept is the main thing. Calculation, there may be very little differences. So anyway, the thing is that we can find out H8. So explicitly M1 is known. Similar way I can know M2 by the energy balance of this heater, if we consider a control volume around this heater. Let us write this, then M2 into H3. So this is the inflow. Another inflow is this one. What is this? 1 minus M1 into M1 minus M2, because this water amount is 1 minus M1 minus M2, which is coming at enthalpy 6, and the outcome is 1 minus M1 into H7. Now you see H3. What is H3? It is known. Bleed pressure is known. Okay. Isentropic expansion, we know H3. What is H6? Similar way H6 we can find out from H5 minus H6. Sorry, H6 minus H5 is P6 minus P5 into V5. Clear? H6 we know. Now H7 is the, again simple one, the saturated water enthalpy at this pressure. That means we will have to very carefully calculate this H1, H8, H9, this thing from the use of steam tables or Molière diagram, and then can find out M1, M2. So the determination of M1, M2 by making use of the energy balance over at the heaters, energy balance enveloping the heater, considering heater as the control volume over the heater, we can find out M1, M2. When M1, M2 is known, then we can make the analysis of the cycle parameters on the basis of 1 kg. This is also basis of 1 kg, and you get the result. So this is the net work output per 1 kg of steam flowing through the boiler, or per 1 kg of steam at the entry to the turbine. Is it clear? The analysis is as simple as this thing, and this is only in your course. Let us be more friendly or easy with the calculations if we follow a straightforward practical problem, an example problem. This theory will be again repeated through a numerical example. Well, example is like that: the net power output of the turbine in an ideal reheat regenerative cycle, sorry, this ideal does not mean that inside the turbine, try to follow, because afterwards the heaters are there. This ideal means the processes are ideal, isentropic expansions, and there is no heat loss from the heater, heat is transfer taking place between the steam and water, that is why it is ideal. Cycle is 100 megawatt, the net power out. Steam enters, there is reheat regenerative. So you see, this is not only regenerative, this is a reheat and also regenerative. Oh, this is a reheat and regenerative. The steam enters the high pressure turbine at 90 bar, 500 degrees, 550 degrees Celsius, alright. After expansion to 7 bar, 90 bar is the inlet pressure, after expansion to 7 bar, some of the steam goes to an open heater and the balance is reheated to 400 degrees Celsius. This is the inlet temperature, this is the reheat temperature. After which it expands to 0.07, this is the final pressure, condenser pressure. So what is given? Reheat regenerative cycle, that means both reheat and regeneration is there, because the purpose is different. Reheat purpose is to increase the Dynash fraction and purpose of regeneration is to increase the efficiency. So inlet pressure is 90 bar. Whenever any problem will give this power output, means they will tell how, what is the find the value of the steam flow rate. That means you always analyze per unit mass of the steam at the entry and then you divided it by and you get. So this is not at the beginning very important. So important parameter is the 90 bar 550 degrees Celsius, that means inlet condition of the steam. Then intermediate pressure 7 bar and the steam is reheated. Some of the steam goes to an open heater and the balance is reheated. Balance is reheated 400 degree and then expands to this. Alright, this is the problem. What we have to find out, what is the steam flow rate? I told the steam flow rate to the HP turbine. What is the total pump work? All these things are now known to you. Calculate the cycle efficiency. If there is a 10 degree rise in the temperature of the cooling water, what is the rate of flow? This I will come afterwards. At a time, all these things. Now, what is the steam flow rate to the HP turbine? What is the steam flow rate to the HP turbine? What is the total pump work and the cycle efficiency? Let us see this. Now, please. Sorry, this is a wrong diagram. हो गया? हो गया? Huh? Now, this is this situation. Now, this is the boiler, this is the turbine. Now, boiler, this first one, point 1, which is 90 bar and 550 degree Celsius. So, after expansion, this is the HP turbine, HP rather, turbine T. This is LP turbine, LP. Now, after this, the steam is bled off and the rest is going to the, some steam is bled off and some steam is being reheated. So, therefore, there is some steam is bled for this and rest is reheated. You understand? So, some is reheated and some is being bled. So, this is 1 kg. All right. So, that then what happened? So, this is being reheated and goes to LP turbine. So, this is the heater. Then it is expanded to condenser. Then this is the 0.07 bar. You just check whether I am doing correctly or not. So, this is the cooling water supply, just show it. Then this is the feed pump 1, which feeds the water to this heater. Then this heater gets this some M1 kg lead, M1 kg, okay, is being bled. Okay, then 1 minus M1 kg is being going to the reheater. Then it mixes, then ultimately 1 kg. Then this is feed pump 2, and then this goes to the boiler. Okay, let this point is 1, this point is 2, that means 1 to 2, then this is M1. I am sorry, this is not the correct figure. So from 2, let 2 is this point. It may not be disaturated case, it may be here, that depends upon the condition. That will come as a solution of the problem. First of all, draw the diagram in TS, draw the cycle in TS diagram for your understanding. This one, yes, very good. So this comes at 1 in the HP turbine. After expanding to T to 2, some is going to reheater and some is coming for the bleed. That means M1 kg is coming straight for this and 1 minus M1 kg is going. That means here 1 kg, that means start with 1 kg, here it is 1 kg. So 1 minus M1 kg is going and M1 kg is going for heater. You understand? So 1 minus M1 kg is reheated to 400 degrees Celsius. So that means this temperature is 400 degrees Celsius. This goes to the LP turbine and expanded to 0.07 bar. Clear? Then 0.07 bar steam, that is 1 minus M1 kg, is pumped to this pressure, P2 pressure. I am not showing now the point will be shown afterwards. So this 1 minus M1 kg is being fed to this heater. This will get M1 kg and 1 minus M1 kg, they come as 1 kg. Okay? Now this 1 kg of water is being again pumped to the boiler pressure and it goes to the boiler. Alright? Now come to this 1 to 2 is this point. From 2, M1 kg of mass is being bled. But from point 2 there is a reheat, 3. That means which one will be 3? This one, this point 2. Okay, so this will be 3. But this 2 to 3 is associated with 1 minus M1 kg. Then from 3 you draw here, it should be within this wet region. That is 3 to 4, that means this point 4, this is the 4. Clear? This point is 4. So after 4 it is condensed, so this point is 5, that means this point is 5. So therefore this is 1 minus M1 kg, earlier I have written. So 1 minus M1 kg. Now this feed pump 1, this is the feed pump 1 process, which gives 5 to 6. 6 is which one? This pressure line. Now it is heated with this blade steam and this point is 7, that means this outcome is 7, and this 7 point corresponds to 1 kg of mass, because 1 point M1 meets with M1. Then 7 to 8 is this 8 is the boiler pressure. So this is the heating in the boiler. Clear? Earlier also the diagram which I showed you, here also I have forgotten to tell that this is the heating. That means in this case the average temperature of heat addition is not only T1 to T10, which is much higher than T1 to T5. You understand this? So here also the temperature of heat addition is like that. So this point is clear. So the problem is clear in its block diagram, and also this is wrong, this is nothing, and also in the TS diagram. Any question? Clear? Now how to solve this problem? If you open this steam table, it may be little difficult. So therefore always I will prefer that HS diagram. Let us see that HS diagram. Let me first draw the HS diagram. Well, let me draw the HS diagram. This is the constant pressure line, and let me draw the constant temperature line. These are the constant temperature lines. These are constant temperature lines. These are constant temperature lines. And let me draw the, what are the things that is there in the constant X lines. Alright. Now how to do the problem? Now first you select this point 1. let us consider this temperature is 550 degrees Celsius and this pressure is 90 bar. That means I find out the intersection point. That means this part I am generating here. That is the only thing in HS diagram. Then what I do? I just go on expanding it up to what intermediate pressure? 7 bar. Let this is 7 bar. Don't mind, this is not in scale, so 90 bar to 7 bar. So, because other pressures will come, so 1 to 2. That means I can generate the point 2. That means the point 2, this point 2, oh, this point 2. Clear? Then 2 to 3 is the constant pressure reheating to 400 degrees Celsius. Let us consider this. This is 3. That means this is 400 degrees Celsius.
So this is for one part of the steam.
One part of the steam. Yes. Here I am drawing the process. So mass is changing. Very correct. It is the representation of a process. Mass is changing. One part of the steam. And another part of the steam is going where? Another part of the steam. This is another part of the steam is also cooled down. This is the mkg and then this is being cooled like this. And this part is not here. It's not shown in the usual Molière diagram. So you are not interested with. That means this is the part, this part is for M1 and this part is for 1 minus M1. Or if this part is M1, then this part is 1 minus M1. Hardly matters. So you understand? So 3. Now from 3 to 4. So let this is the 0.07, this pressure line, which is not in scale, 97 and 0.07. That means I simply grow to this. So I can find out also dryness fraction. That means this is my 4. So 1, 2, 3, 4, 1, 2, 3, 4 I draw. Very correct. 1, 2 is associated with 1 kg. 2 to 3 is 1 minus M1 kg, whether M1 kg is being cooled in this direction. 3 to 4. Because my intention is to find out H1, H3, H2, H4, which will be required in the calculation, which is directly read from these ordinates, straight by drawing these lines. Rest is very simple. You calculate the M1 by the energy balance for this heater. You calculate and then you can find out what is required. What is the steam flow rate? Means we have to find out WT minus WP. What is WT? Please tell me, space is not there, I cannot write all. WT here I write, WT here. WT is what? H1 minus H2, very good, plus 1 minus M1 into H3 minus H4. And all these things, H1, H2, H3, H4 are directly known. What is WP? WP, there are two pumps, one here, another here. This pump handles 1 minus M1 into H5 minus H6 and H6 minus H5, very good. And another one is 1 into H8 minus H7. Now you see from this diagram, ठीक है?
So will you please repeat what is WT? So 1 minus M1 into 8.
6 minus H5.
No sir, that is sir not for WP. Sir, I am saying for WT.
WT, H1 minus H2 plus 1 minus M1, H3 minus H4. Clear? Now here H6, what is H6 and H5? H6 and H5, H5 is, now it is from steam table. You have to calculate both, you have to do with both. This part is easier for this, but steam table directly will give the value of H5. H6 you can find out from the same principle. H6 minus H5 is P6 minus P5 into V5. Okay, H6 minus H5 is P6 minus P5 into V5. Similar way. So you know H6, H5 you know, H8, H7, H7 you know, because you know this pressure, H7 you know. These are from steam table. And again you know H8 by the same thing. H8 minus H7 will be P8 minus P7 into V7. Now when you know WT, WP, you can find out this per 1 kg of steam going through this. The total power is 100 megawatt. Divided, did you get the steam flow rate? Now next is the what is the total pump work, alright. So for 1 kg of HP turbine flow, this is the power. So for just reverse 100 megawatt, primary school level thing. You have to find out the steam flow rate to the HP turbine. For 1 kg of steam flow to the HP turbine, you get this power. For 100 megawatt power, steam flow rate. Okay, alright. That means 100 divided by what you get. This is the specific work output. Specific means per 1 kg flowing through HP turbine. So first part is over. What is the steam flow rate to the HP turbine? Second is what is the total pump work. I think I don't have to repeat, you can solve this. Total pump work. Total pump work is this. So how to do the problem? That you have to find out M1 by making this energy balance across the liter for 1 kg. But when you know this kg of flow rate, you can find out, multiply the total pump work. So if you do on the basis of 1 kg, then you will land up to the answer that this is the total pump work per 1 kg of steam flow through HP turbine. For examination I may deduct few marks, but actual answer will be the total mass flow M1. This M1 is per 1 kg. So you understand. So therefore the pump work is for 1 kg of flow to the HP turbine. Already I have found out the steam flow rate through the HP turbine, multiply that. That means the total pump work. Like that total net work is given. Okay. Alright.
Yes, sir.
Understandable. Then cycle efficiency. Very simple. Cycle efficiency, for that you don't require the mass flow rate. WT minus WP divided by H1 minus H8. Okay. Now next part is simple. What is that? Heat transfer. If there is a 10 degree rise in the temperature of the cooling water, what is the rate of flow of cooling water in the condenser? The rate of flow of cooling water in the condenser is the condenser heat balance. M dot Cp into this delta T is equal to the heat lost in the condenser. That means H4 minus H5 is equal to mass flow rate in the mass flow rate. That means this part is very simple. M dot into Cp into delta T, which is 10 degree, equals to H4 minus H5 into 1 minus, very good, into 1 minus M1 into H4 minus H5 into the mass flow rate of the HP turbine, HP M dot HP turbine. Because I will have to find out the mass flow rate of the cooling water. Otherwise, if you suppress it, the result will be this is the mass flow rate of the cooling water per unit steam flowing through the HP turbine. Next part, if the velocity of steam flowing from the turbine to the condenser, that means the LP turbine, turbine to the condenser is limited to a maximum of 130 meter per second. Find the diameter of the connecting pipe. How to? So mass flow rate is rho AV. Rho is, in fluid mechanics we write like this, but here we write small v. This v is the velocity. So therefore you know V4. This velocity is given, velocity of flow. So you can find out the area. So that is the diameter of the connecting pipe. Clear? Hello? Arey Baba, this is the continuity equation, forgotten. Okay? Okay, yeah.
But in that case, the value of the M dot should be the M1 dot, sir.
The value of the M dot, oh, I have not the, yes. Value of the M dot is, that is 1 minus M1
1 minus
into the mass flow rate of this thing. That means this is per unit mass flow rate. Mass flow rate to HP turbine. I am sorry. M1 is the fraction per unit mass. So 1 minus M1 into mass flow rate of the HP turbine. Everything is known. That is the actual mass flow rate. Very correct. I am sorry. The space is so small, so at a time this cannot be displayed. If it could have been a blackboard, could have been a much better scenario. However, this is okay. Now here I end this. I end this discussion on these cycles I think the ideal cycles have to start, but I do not know whether I will get time today. However, now we will go to the
Sir,
analysis of, please.
sir, is there any method to calculate the mean temperature during the ideal during the this non-ideal regenerative cycle? To calculate the mean temperature.
Mean temperature of what?
Of the heat transfer during the of the heat addition.
Yes. His question is that how to calculate the mean temperature of heat addition without regeneration, or what? With regeneration.
No, sir, with regeneration.
For any, now that I tell you, for any heat transfer process, again I repeat, for any heat addition process, it is a good question. I think we can discuss this because the ideal air standard cycle we can take after. Let us consider a heat transfer process in general, whatever is there. In general, a heat addition process where this system changes from state 1 to state 2, where the temperature increases, heat is added. That means this is the process where heat is added. Let us describe a heat addition process, reversible heat addition process in a TS diagram, heat addition Q1. So, where T2 is the temperature, final temperature, T2 is greater than T1. So, heat added Q1 is equal to H2 minus H1, which is not read in this axis. So, in HS axis we can read. So, this is a varying temperature heat addition process, not an isothermal heat addition process. Heat is added, so system increases its temperature from 1 to 2, and obviously there is an increase in entropy. A mean temperature Tm, that is Tm, is defined as H2 minus H1. This is a question which can come in the examination also, H2 minus H1, which means that this graphically this can be explained like that. Now, this area, let this is AB, 1 to BA is the area which represents the heat transfer during the process 1 2, because we know delta Q is TdS. Therefore, Q is integral of TdS. Integral of TdS 1 to, that means the area under this curve. And if I draw a rectangle with this ordinate as Tm, that means this value of Tm, so a projection like this, that means if I can construct an ordinate such that this area, that means now AB, CD, if I can draw a parallel line to AB, CD at such height, simple school, primary school geometry, so that the area ABCD becomes equal to the area 1 to AB, then this ordinate will read as mean temperature. That means this is the mathematics, the mean temperature of heat addition. That means the physical definition is that the mean temperature of heat addition in any varying temperature process is a constant temperature. That means the temperature at which, if heat was added at that constant temperature, it is a constant temperature at which heat was added. That means the temperature at which, if the same heat was added, could have given the same entropy change. You understand? That means the same heat added could be expressed as Tm into S2 minus S1, because this is the area DCBA. Because at constant temperature, heat addition is T into S2 minus S1. So, this is the way one can calculate the temperature, mean temperature of heat addition. Similar is the case for heat rejection. If this could have been a heat rejection, the same diagram from 2 to 1, we could have found out like this. Okay. So, this is the way one can find out the mean temperature of heat addition. Now, today I will close the lecture, but before that I will tell you next class I will start the air standard cycle. Today some time is there, so I will not start any calculations, but I tell you what is an air standard cycle or gas power cycle, not air standard, gas power cycle. Now, I have already discussed earlier that a power cycle means the thermodynamic cycles where power is being obtained at the cost of heat energy. So, this is a power cycle. When the working fluid changes its phase during the operations in the different processes of the cycle, this is known as vapor power cycle. The example is the thermal power plant, where the working system water changes its phase. Now, a large class of practical power plants uses gas. So, therefore, these power plants, the cycles, the theoretical cycles of these power plants will be gas power cycles. For an example, gas turbine power plant, where the air is burned, so where fuel is burned in air and the products of combustion in gaseous phase works and gives you the power in a gas turbine plant, aircraft engine, automotive engines, that means your automobiles. So, there we get mechanical power and working system is a gas. That means the thermodynamic cycles which gives mechanical power is the power cycles, the cost of heat, and the system is gas, we call it gas power cycles. But basic definition of a thermodynamic cycle is that the initial state and final state should be same. That means all the state properties and state variables have to be identical. Mass is one important property. So, if the mass of the system changes or even the constituents of the system changes during the cyclic process, even the pressure temperature comes to the same value, it does not follow in actually the definition of a cycle, because the cycle means the mass has to be same. So, therefore, in all practical power plants, they do not actually reveal actually a thermodynamic cycle, because mass is changing. Some part it is air and some part it is the product of combustion where fuel has been burned, so that the mass has changed. And moreover, the products of combustion, the gases, their compositions are different from that of the air, because the mixture of air and burnt products of the fuel. So, therefore, these are not actually cycles by definitions. There are other reasons by which the definitions of cycles are violated. Why? The basic definitions of heat engine cycles are there. There is an external source from which heat is added to the working fluid, which is being closely followed by a power plant. That steam is the working fluid or water is the working fluid, where heat is added from outside. That heat source is the gas, which is known as flue gas, that is the product of combustion when the fuel, which is largely the coal is burned, or sometimes liquid fuel is burned, and the products of combustion. They are not the working system. But most of the gas power cycles, for example, gas turbine cycles, as you know, these are now today popular knowledge, that in your automobile cycles also, the products of combustion itself is the working system. You understand? So, therefore, there is no heat addition from outside, rather a chemical energy is being into thermal energy, and they carry this thermal sort of heat. Heat cannot be carried, actually heat is an energy which can be transferred because of a temperature difference, but that carries the thermal energy which acts just like heat, and because of the processes we get work. So, therefore, this what I will call the cyclic operations do not conform to an actual thermodynamic cycles. So, therefore, there are certain therefore, what happens, these power plants are being approximated by a theoretical cycles which follow all the definitions of a thermodynamic cycle, proper thermodynamic cycles, and where air is used as the working fluid throughout the cycle and heat is added from outside and rejected to the atmosphere. That means this burning of the fuel which generates the thermal energy, we loosely tell the generation of heat, which is a loose term because heat cannot be generated, it is an energy in transit, but generation of internal energy, whatever you call high temperature, this is being simulated by a process where air is the working fluid and it gets heat from the outside. So, these are the assumptions which are made, and air as an ideal gas is considered to be the working fluid of a thermodynamic cycles, and they approximate or they represent the theoretical cycles of these power plants known as air standard cycles. So, what is the difference between air standard cycles and the actual cycle? Everybody, all of you know that automobile petrol engine runs with Otto cycles, but Otto cycle is an air standard cycle, so where the working fluid is air and the processes that ideal processes, but in actual automobile cycles, the cyclic operations which are performed in practice, there the working fluid is not air. Initially air is sucked, then fuel is burned, then the fluid becomes, the working system becomes the products of combustion and the air, and also the processes are not ideal. These are always there. Process cannot be isentropic or constant pressure process cannot be maintained. There is a pressure loss and all these things. So these are being approximated by the cycles which have all ideal processes. Heat transfer takes place by heating from an external source, okay, and cooling to an external sink, and air is the working fluid behaving as an ideal gas with constant specific heats. Those cycles are known as air standard cycles, then they are the theoretical cycles for those gas power plants, and we will discuss those air standard cycles in next classes, next following few classes. Clear the concept of air standard cycle. So I think I will stop today, and any question you please ask. Any question? Okay.